let us look at some examples related to the Krull-Schmidt theorem. So first example, what is the Krull-Schmidt decomposition when we look at finite abelian groups? Or maybe I could even say a little more generally, finitely generated abelian groups. Or what we are also talking about are finitely generated Z modules. We want to say it in the language of modules. These finitely generated abelian groups satisfy both the ascending chain condition and the descending chain condition, and therefore the Krull-Schmidt theorem applies. So let's just see how the Krull-Schmidt theorem works for this class of modules. So suppose A is a finitely generated abelian group. Then define its P primary part to be those elements A in A such that P to the n A is 0 for some n greater than or equal to 0 for a fixed prime P. So for each prime P you make this definition. Then we know from the theory of finite abelian groups that A is isomorphic to Z to the power n direct sum, and then there's a sum over all primes P AP. And this part, there are only finitely many non-zero, AP is non-zero for only finitely many P, and so this is going to be a finite direct sum. So all this follows from the structure theorem of finite abelian groups. In fact, from this decomposition, you will be able to see that A satisfies the ascending chain condition and the descending chain condition. So if A is indecomposable, either A is isomorphic to Z, or A is AP for some P, for some prime number P. So either A is free and it's isomorphic to Z, or A is what is known as P primary for some prime P. And furthermore, if A is P primary, then the structure theorem for finite abelian group says that A is isomorphic to Z mod P to the lambda 1 Z plus Z mod P to the lambda 2 Z and so on, Z mod P to the lambda L Z for some integers 0 less than lambda 1 less than or equal to lambda 2 less than or equal to lambda L. And in fact, these integers are uniquely determined, and that's a consequence of the structure theorem for finitely generated abelian groups. Now, in this decomposition, the uniqueness of these integers P1, P2, PL can also be viewed as a consequence of the Krull-Schmidt theorem. We've already seen that every indecomposable finite abelian group is in fact of the form Z mod some prime power, and this is exactly a Krull-Schmidt kind of decomposition, and saying that when arranged in weakly increasing order, these invariants lambda 1, lambda 2, lambda L are uniquely determined is in fact the statement of the Krull-Schmidt theorem. So uniqueness of lambda 1 lambda L is a special case of the Krull-Schmidt theorem. Let us look at another example that we have encountered in Algebra 1, which is finite dimensional modules over a polynomial ring. K is a field, and when we say finite dimensional, we mean finite dimensional over K. So this is also known as so finite dimensional KT modules are in bijection with matrices. I'll recall how this works in a bit, but you've seen this in Algebra 1 if you took Algebra 1. So suppose M is a finite dimensional KT module. And take PT to be any irreducible polynomial in KT. So by this I mean irreducible polynomials in KT. Then define again the P primary part. MP equals M in M such that Pt to the power n times M is equal to 0 for some n greater than or equal to 0. Then again we know from basic module theory that if you want you can go back and look at the lectures on finitely generated modules over PIDs. M is going to be direct sum over P in irreducible KT MP. And once again, this M being finite dimensional, only finitely many of these MPs will be non-zero. And so this sum will actually be a finite direct sum. So you get a canonical direct sum decomposition of M. There's no choice here. Okay, and but then each MP need not be indecomposable in general, but certainly if M is indecomposable, then M is equal to MP for some P. So if M is indecomposable, then M equals MP for some polynomial, irreducible polynomial in KT. Moreover, by the structure theorem, M is isomorphic to KT mod PT to the lambda 1 plus KT mod PT to the lambda L. And this again here we have 0 less than lambda 1 less than or equal to lambda 2 less than or equal to lambda L. And the uniqueness of these invariants lambda 1 to lambda L is again can be viewed also as a consequence of the Krull-Schmidt theorem. And in particular, the indecomposable KT modules M is isomorphic to KT mod PT to the power lambda for some lambda greater than or equal to 1. Okay, so these are precisely the indecomposable modules. Let's take a special case when K is algebraically closed. In this case, Pt has to be of the form T minus alpha for some alpha in K. Here I should say that these PTs are only, maybe we should say here, let's just to make this unique, we don't want to consider a polynomial and some K multiple of that polynomial. So maybe here I should say irreducible monic polynomials. So we'll only take polynomials with leading term equal to 1. And so likewise here, every irreducible polynomial is linear, and by scaling it, we can make it monic, and hence of the form T minus alpha for some alpha in K. And in that case, M is isomorphic to KT mod T minus alpha to the power lambda. Now, if you take a basis, one T minus alpha to the power lambda minus 1 for M, then multiplication by T has matrix given by 1 alpha 0 0 1, and so you have, no, I think I got this wrong, it's alpha 1 0 0 alpha 1 0 0. So you have alphas along the diagonal, you have ones just below the diagonal, and everything above the diagonal is 0. This is what is known as a Jordan block with eigenvalue alpha of size n. And so in decomposable KT modules correspond to Jordan blocks, at least when K is algebraically closed. Now we can turn this thing backwards, and we can also say that given a matrix n by n matrix in K, we can form a KT module. So we just take MA to be K to the power n and make it a KT module by allowing T to act by K. Or so what I'll say is by setting Ft times a vector V to be Fa V. So this Fa means you take the polynomial f and divide, so f is a polynomial with coefficients in K, you substitute for the variable T the matrix A and evaluate it. You will get an n by n matrix, and you can multiply it on the right by any vector V thought of as a column vector. Now, using this correspondence between matrices and KT modules, we can transfer ideas from module theory to matrix theory. So here are some definitions motivated by this. A matrix is simple if MA is simple. We could say a matrix A is indecomposable if MA is indecomposable. And let me just introduce a new notion. A matrix A is simple, semi-simple if MA, a module is said to be semi-simple if it is isomorphic to a direct sum of simple modules. So is a sum of simple modules, is a direct sum of simple modules. So for example, if A is simple, then that means that MA, we just seen, is isomorphic to KT mod PT for some irreducible polynomial PT. Irreducible monic polynomial PT. Well, we didn't quite see this, but what we saw is that if M is indecomposable, then it is of the form KT mod PT to the N. And since every simple module is indecomposable, it's not difficult to see that the only simple modules among KT mod P to the N are the ones where N is equal to 1. So modules of the form KT mod PT. And what this means is if you taking basis 1 t to the power d minus 1, where d is the degree of PT, we get that A is similar to the matrix, which has the following form. So the first basis vector is 1, it goes to the vector T. So it starts off like just with ones in the row just below the diagonal, and so you have this last column left, and there you put in the coefficients of PT. So you put in minus A0, minus A1, minus A sub n minus 1, where PT is equal to A0 plus A1t plus an minus 1 t to the power n minus 1 plus t to the n. We are assuming that PT is monic. So that's what simple matrices are always similar to companion. This is called a companion matrix of PT. Simple matrices are similar to companion matrices of irreducible polynomials. If the field K were algebraically closed, then PT would have degree 1, and this would just be a 1 by 1 matrix. Now let's look at what happens to indecomposable modules. If A is indecomposable, then that means that MA is isomorphic to KT mod PT to the power n for some n greater than or equal to 1. Okay. Now if K, it could have a slightly complicated form, though in most cases, especially when K is a perfect field, it can be simplified. But for now, I'll just keep this simple, and let's assume that K is algebraically closed. Then what we've seen is that just PT has to be of the form T minus alpha for some alpha in K, and what we get is that A is similar to A1, this Jordan block of some size. Of size n here. And finally, let's look at the case where A is semi-simple. In this case, A A is similar to, well, it's a direct sum of simples, and so A is similar to CP1, CP2, a block diagonal matrix where the diagonal blocks are companion matrices of irreducible monic irreducible polynomials. And if K were algebraically closed, this would mean that A is similar to alpha 1 alpha K, because these irreducible polynomials would be of the form T minus alpha 1, T minus alpha 2, T minus alpha K for some alpha 1 up to alpha K in K. In other words, K, the semi-simple matrices in an algebraically closed field are precisely the diagonalizable ones. Okay, I'll end this session with a very interesting example, which is called the proofer group, which we have briefly encountered during one of the lectures. So this is a Z module, it's an abelian group. So the definition of this proofer group, which I'll denote by P, is, well, it's the P primary part of Q mod Z P, of the group Q mod Z. What is this? So these are those elements of Q mod Z which are killed by some power of P. Now, if you ask what are the elements of Q mod Z that are killed by P, then that's 1 over Pz mod Z. What are the elements that are killed by P squared? That is 1 over P squared Z mod Z. What are the elements that are killed by P cubed? That's 1 over P cubed Z mod Z. So, of course, this is an increasing chain. 1 over P squared contains 1 over P squared Z contains 1 over Pz, 1 over P cubed Z contains 1 over P squared Z, and so on. So this is an increasing chain, but what we want is an infinite union, and that will give you the full proofer group. So what I'm saying is that the proofer group P is equal to union n greater than or equal to 1 over P to the n Z mod Z. So this is an increasing union of subgroups of the proofer group. And this group 1 over P to the n Z mod Z is, of course, just isomorphic to Z mod P to the n Z, just scaling everything up by a factor of P to the n. And this is not finitely generated. And it doesn't satisfy the ascending chain condition. Well, that's obvious because here is an ascending chain which never stabilizes. And it's not finitely generated because if you took any finite subset of P, it would be contained in one of these subgroups, and so it could not generate all of P. Now I claim that P is indecomposable. Suppose that, so what we need to show is that if P can be written as a direct sum P1 plus P2, we need to show that one of these is equal to P and the other is 0. Then, but we can't have both So how to show that one of them is equal to P? Now if P is P1 plus P2, we cannot have that both P1 and P2 are finite, because then P would be forced to be finite, but it's clearly infinite. So then either P1 or P2 is infinite. And I'll show that whichever one is infinite is going to be all of P, and the other one has to be 0. So let's say that say P1 is infinite. So then what we have is that since P1 is infinite, P1 cannot be contained in a finite subgroup, so P1 is not contained in 1 over P to the n z mod z for any n. Okay, so that means that there exists an element A mod P to the m in P1 where AP, the GCD of A, and A is not divisible by P, and M is greater than N. Right? Any element which is not of this form could be further reduced to the form where A comma P is 1, and then if the M is less than or equal to N, then we would have it inside this subgroup 1 over P to the n z mod z. So there exists an element of this form. Since A comma P, the GCD of A and P is 1, the GCD of A comma P to the M is also 1. So there exists an integer B such that AB is congruent to 1 mod P to the M, P to the N, let's say. So what I can do is I can write AB, maybe I should say AB is congruent to 1 mod P to the M. So AB mod P to the M is going to be equal to 1 mod P to the M in the proof of group P. And so 1 mod P to the M belongs to this P1, which also implies that P1 contains 1 over P to the n z mod z. This is because every element in 1 mod P to the n z mod z is a multiple of an integer multiple of 1 over P to the m. So since P1 is a subgroup, if it contains this element, it will contain every multiple of it, and so it must contain this. So what we see is that P1 contains 1 over P to the n z mod z for all n greater than or equal to 1. But this clearly then implies that P1 is equal to P, because P is precisely the union of these subgroups, and P2 is 0. So this means that the proof of group P is indecomposable. Now here's a small challenge for you. What is this local ring NZ of the proof of group? Okay, with this, I'll stop.